Okay, so today our speaker is David Spergel from Simons Foundation, and perhaps the best way to introduce him is to mention a few things he has done. For example, everybody knows that Earth goes around the sun goes around the center of the galaxy, but it was David at a tender age of 20-something that realized how important this fact is, because it means that in June we will get more dark matter detections than in January or something, right? So we haven't detected yet, but when we do, this will play a major role, this yearly modulation. Another thing which I personally used in my work was this crazy idea that dark matter is a solid. Can you believe this nonsense? But it actually makes sense, apparently. And of course, David really did a huge work when he extracted all this cosmological data from the Wilkinson probe of relic radiation. And for that, he was rewarded by being promoted to some high administrative work, so he only has Fridays now to do good things, but then the rest of it is also sometimes good, like helping Ukrainian scientists and stuff like that, which is of course very valuable. And as for you, Glenis wanted me to say something about producing or whatever. Maybe you can do it.
So I'll just skip mine. So it's fun to be here. I was thinking about the first time I came to NYU. I was a college senior working with Jill Knapp. Patrick Huggins organized a workshop on planetary nebulae. And that was the first meeting I ever went to as a scientist, because I had done my thesis on that talk. Patrick, I think those who've been around longer remember him, great guy who passed away too young, too quickly. Been here many times for talks. I think my last colloquium here was in 2014, and I came up and on the train I knew I was giving sort of a CMB overview, and in the overview there was just been this bicep result, and I had decided, okay, if I'm giving a talk, I better read the paper. So I took the train on the train from Princeton to New York. I read the paper. I was working on dust. No. And I realized that they had improperly calculated the throw of dust. They just made, in some ways, there's many errors in that paper, a lot of things wrong with it, but there was sort of a factor 2 error, which meant 4 in power, and it was off. And then towards the end of my talk here, I said, I have my doubts about the result, and talked about why.
You better tell for the non-particle people what that is.
So the bicep experiment claimed that they made a detection of primordial gravitational waves of the early universe. And this was a really big deal back in 2014. Those of you who were around then remember it. The students, it's now forgotten, right? This was front page of the New York Times, 2,000 papers citing it within 3 months.
This was proof of inflation.
It was the proof of inflation. There's an infamous film of Andre Linde, being incredibly excited. Defend Andre. A TV crew shows up outside your door and says, inflation's been proved. You get excited. Right, that's legit. I gave a talk here and said, I think it's all dust at the end of the talk, and I thought that they had improperly misinterpreted it. And I had signed then, as I did now, that my talk would be posted to the web. And what I had not appreciated at that point was the power of Twitter, or the power of David Hawk.
I think it was my fault, I apologize.
And all worked out. So David tweeted something about my saying that it could all be dust, and with the link to the talk. The next week, I was the colloquium speaker at Harvard, and I got there, and everyone was angry. I said, what? You said your talk, it's all dust. We all watched your talk. I was like, everyone is watching the end. I mean, this is a great place, but like I didn't imagine the entire Harvard faculty sat around watching this video rebroadcast on YouTube. But they did. And John Kovac was particularly annoyed with me. And I went to John's office, and you have to understand, John was my senior thesis student. So I knew John for a long time. And I went and spent 2 hours with John saying, here's the tests you need to do to prove it is not dust. And he, of course, had the data. I made some estimates from their paper, and I went through and came up with a list of things. And then when I can, I try to take the train. So I took the train from Boston back to Princeton. And on the train, I wrote an 8-page email about all the tests he needs to do. And those of you who know, who have corresponded with me on email, knows like my goal in email is to keep my emails to like 1 word. Because I get a lot of emails these days. So I try to be efficient. So an 8-page email for me, it's probably the only time I've ever written one that long. And he didn't answer it. Advice to young people. When your thesis advisor writes you an 8-page email, answer it. So I then went on to, actually a lot of the real work done by Raphael Flather and Colin Hill to reanalyze that work, and we showed it really was all dust. And when the Planck results came out, they agreed with what we said, and the paper was effectively withdrawn. And it's actually, I think, a story of, mostly speaking, the way science is supposed to work. People make ambitious claims. Those ambitious claims are checked by others, and eventually we find out whether the result is wrong or right, and we get more data, and that's the way things go forward. So I think this talk will be hopefully interesting, but neither the first talk I've ever gone to in my life, where I sat in the back somewhere, nor, though it wasn't in this building did not exist when I was a undergraduate, nor will it be that, I think, well, I hope it will not get people as angry as the previous one. Though who knows what Hog will try.
By the way, one side note is that there was an anthropologist here visiting me that week, and that the story of that whole story appears in an anthropological study of cosmology. I'll forward it to you.
Oh, interesting.
It's quite hard to read because it's written in anthropological language, but you're the star of the show of an anthropological study of cosmology. That started because he happened to be visiting that week.
He's a subject, not a star.
Well, right, he is the subject, exactly. He is named though.
Yeah. And to summarize, as I said, what do I do with my other 80% of my time? Well, I like to describe what I do at Simons Foundation. I have so many different roles. I'm a publisher, a now Pulitzer Prize winning magazine, Quanta, publisher of another magazine on autism, president of a film company for Fire of Love, which is at the Academy Awards this year. It's now showing in theaters near here. It's a great film. It's a love triangle between 2 volcanologists and a volcano. Does not end well for the volcanologists. I run a small real estate company because we have the Alabama on it, so I get to learn about plumbing leaks. I am president of a biotech company developing autism drugs. I learn about autism tests and FDA tests for drugs and things. And that's like 20% of the job. And the rest is, it's working with Flatiron, it's learning things. It's actually a really interesting job because it is an opportunity to do things like when something happens in Ukraine to help Ukrainian scientists and then thinking about ways in which we can have impact. So that's my day job. This is now my hobby. And tell you about what we've been doing. I decided, because we're just about to put out results, to give people a sense of some of the things we're learning, to focus primarily on things that are coming out with the new ACT data set. And a lot of these slides, let me thank Will Colton, Blake Sherwin, Sigurd Ness, and Manu Shan, who provided some of the slides here. And overall, let me really thank the ACT team, and particularly highlight Susan Staggs from Princeton, who's leading the science team, Joe Dunkley, who's leading the analysis, Sigurd Ness, who is produced the maps you'll see. And what I'll be teasing is our data from our upcoming release, and we will have results out soon, what we call DR6. That's 16,000 square degrees of the sky. So that's sort of half the non-galactic sky at high resolution, 5 times the resolution of the Planck experiment, 10 times more data than they see in the experiment. And just, you can see the progress in both sensitivity and resolution. Planck experiments, phenomenal experiment. Here's the Planck results at 3-scale resolution. See the CMB fluctuations. Here's ACT at the same, with some of the longer wavelength modes filtered out. You can see much more sensitive small scale measurements, and then lots of small scale stuff. And what you're looking at in that small scale stuff are both AGNs, which appear as hotspots, and clusters, which at these frequencies, clusters of galaxies, appear like cold spots. They're shadows against the microwave sky. And we have thousands of these. It's kind of amazing every time you look there, you can then look in the optical sky and see a cluster. And what's nice about the thermal SC effect, and just remind you that that effect is proportional to the integral of the pressure along the line of sight, or y. And when you measure across the cluster, that's just really measuring the PdV of the cluster, which was effectively proportional to the mass. So this gives us a mass selected measurement of clusters across much of the visible universe. And what I want to talk about today is all the different ways in which, as the light gets from the surface of glass scattered to us, it propagates through the intervening matter and gives us information in various different ways about it. The lensing signal, which will be the first thing I'll talk about, is going to measure the integrated mass along the line of sight. There's some others I've listed here which we're not going to focus on. I will talk about the thermal Sagan-Soldovich effect, the one I've mentioned here already. That's giving us a measure of the integrated gas pressure. We can also measure effectively the integrated gas density. The polarized scattering also gives us information on the gas density. And I'll show you some measurements that Will Colton has been leading that represents the first measurements of this effect, and also some of Will's work on the relativistic thermal-Sagan-Soldovich effect, where we have the first detection of that effect from clusters in a way that gives us a measurement of the effective, another way of measuring the temperature of the gas of the clusters. So let me start with the lensing work, and this is work led by Blake Sherwin and Frank Koo, and looking at our maps. And the picture to have here is as the photons propagate from the surface of glass scattered to us, they're deflected by large-scale structure along the line of sight. And what that does is it takes the unlensed CMB and distorts it. So you can see the hot and cold spots distorting due to lensing. Now the challenge is we don't have this before picture. We just have the after. And what we want to do is see how the signal has changed. The way we pick it up technically, is here it's all Gaussian field characterized entirely by a 2-point function. This generates a non-trivial 4-point.
So this was real thing, not some artist impression. The actual displacement was real.
The displacement was real. I mean, it's simulated at the right level.
Right,
These are
but at the right amplitude.
And then here you
And
can see-
typical displacement, just for context, typical displacement of a point on the sky relative is what, 10 arc minutes?
a few arc minutes,
A
like
few arc
4 or 5. So characteristic number. So that's an interesting number, which usually you don't get to see. So even when you're looking at a lens galaxy, a galaxy at redshift, say 2, the typical, not strongly lens, just a typical galaxy at redshift 2, it has been displaced by about 2 arc minutes by lensing. But it just gets
You
moved.
measure,
It's
right?
how you
Here
get
you
it.
can measure it.
Here we can measure it because we've got the whole field. Yeah, so here, this is exaggerated in this case. So you can see what it does is, when this arrow is backwards, it shifts power mostly to smaller scales. So it takes the map and shifts the map to small scales. So it shifts power, and you can see it in terms of mode coupling with it. And what we can do is make an estimator for the deflection field by taking the temperature and taking the combination of temperatures here, integrating over L, and that's how we get the deflection.
Is your picture sort of suggesting that the sometimes thought to be anomalously large scale structure is
No,
not?
this is exaggerated. And then what that deflection field does is measure the integrated density. So you're seeing it's looking at, do we have a pointer? If not, I'll just.
It's often stolen.
Nice. Okay. Right, so the deflection field, which we infer, is the integral along the line of sight from the surface of last scattered to us of the density field with a weighting function. And it really is roughly equally weighted along the line of sight. So it's really measuring primarily the integrated density from redshift of 0.5 to 6. So we're basically seeing the projected mass of the universe. And we can either look at that in terms of its map or in terms of its deflection field. And we first detected this in work led by Sudeep Das. Sudeep, who was my student who then went on to Berkeley, turned down a faculty job to go work for what eventually became a career at Netflix. And he's now in charge of choice at Netflix. So when it comes up and says, if you like X, you'll like these other movies. Sudeep, who made the first detections of lensing. To do some of this work, he had to work with really large matrices and figure out how to get eigenvalues and eigenvectors fast. And that turns out to be a similar problem. So, I did not know we were training graduate students to help us get better movies, but the suggestions aren't bad. Why do we want to do this? Why do we want to measure it? Well, there's a couple motivations. One is this intriguing hint that there's something wrong with large scale structure. So if we look at the best fit model to the CMD, and then compare it to structures at large today, we often do this in terms of sigma 8, which is a measure of clumpiness that cosmologists like to use, which is draw a sphere that's 8 megaparsecs around, measure the RMS density. But just a measure of the amplitude of fluctuations. Sigma 8, we'll use that. But the sigma 8 we get from the CMB doesn't really match that well with what we get from large scale structure and detail. And this is basically, we're taking our primordial fluctuations, taking these assumptions and predicting what happens. And if there's something off, there might be something wrong with these assumptions. And that'd be cool. because these are all things we'd like to know more about. And I think, yeah, this is the current state of play. This is what we infer from Planck measurements. This is what we got. Say, man, let's throw out Planck. Let's get a measurement using WMAP and ACT, independent cut on it. Get the same W. Slightly bigger error bars, but all the CMB experiments are here. These are all these different measurements of large-scale structure. These are lensing measurements with 2-point functions. These are various cross correlations. There are different surveys. This is HSC. This is the dark energy survey. This is KIDS. This is comparing these large-scale structure surveys normalized with Planck. This has not gotten the attention of the H0 discrepancy, but this is not just Adam Rees, right? This is not one group disagreeing with the CMB. This is a whole bunch of different measurements disagree. And each one of them is 2 to 3 sigma low. There's some correlation, so it's not that you can add all of them, but there's a lot of independence in those measurements. And this is really intriguing.
David, it looks like a lot of them have plus Planck, and the ones in the bottom, right?
Yeah, a lot of them have plus Planck.
This is plus Planck lensing. So it's using the Planck lensing map
Yeah.
to normalize the amplitude in this one and these two. And these are various cosmological combinations. So people did them, and some of them don't have Planck in, some do. This is sort of a summary of what's in the literature. And it's one you could do a meta-analysis that combines all of them in different ways. What we've done is we've done a better measurement. So we will have a CMB lensing measurement of sigma 8 that will show up here or here. Not only that, this is one of these teases where we have the result, but I can't tell you.
Can you tell us how big the error bars will be?
Yeah, I'll show you later. What's the mass of the neutrino is another question. I'm going to think of it this way, which is if you take the standard theory as right, one way in which you lower sigma 8 is if the neutrino is massive, it clusters less. And as the neutrinos become massive, that reduces the structure. And we're getting to interesting limits. So this is where we are today in terms of the published literature, in terms of the lensing power spectrum. These are measurements from Planck here, ACT pole, our colleagues the South Pole, and this is improving. And we're now going forward from there. And we've got these new results from ACT. I should note that the ACT telescope is now dead. Having used it for a decade, the motor is broke, and we decided to take it apart. And now pieces mostly sitting in Mark Devlin's lab. The reason we also took it apart is we're now replacing it with a much more sensitive and better telescope with Simon's Observatory. And pleased to report that yesterday, the National Science Board announced approval of funding for MISRI 2 for the Advanced Simon's Observatory. And that will mean that we're at the most, I'll have a plot later on the sensitivities. We're going to get to that more sensitive level. And another cool feature of that is it's going to let us build solar panels for longer operations. So it will be a very green telescope. We'll be operating here. We were going to have to bring diesel a truck of diesel up to the mountains every day to keep the power going, which was expensive, polluting, and also risky just driving that up. And we will be about 95% and 90% solar powered. You still want to have some reserve diesel because there are days when the sun doesn't shine. It costs a lot more to get to 100, but getting to really get very close.
Sorry, suppose you do get some funny sigma 8 which doesn't agree with all the measurements. Can you explain again what's the significance of it? Like what you will measure neutrino mass or?
Well, we will measure that structure. What we will measure with sigma 8 is how much has structure grown from redshift 1000 to today. And if it's grown at the rate predicted by lambda CDM, that rules out lots of alternative theories. If it grows slowly, too slowly, which is what the data is suggesting from the large-scale structure surveys, that requires something that suppresses structure growth. Now, there's actually a lot of different things that suppress structure growth. Neutrinos is one example. Dark energy that doesn't behave like the cosmological constants, another. Modifying GR is another.
But could it be just mishandling of baryon physics, which is usually what happens?
That could be what's going on in the galaxy surveys. The lensing data is telling us primarily about power on scales of about 10 to 100 megaparsecs, where we think baryon physics plays a very small role. So we're now directly measuring the distribution of mass on large scales. So I think it's a more robust and straightforward way than the other techniques. So that's why it'll be, I would say if we see a sigma 8 that matches the Planck predictions and our predictions from our CLs, that to me would say it's baryon physics with the other things. If we can, so our errors are small enough that we will either be able to say we're consistent with the CMB measurements, and that suggests there's interesting baryon physics going on suppressing power in the galaxy surveys, or we will be consistent with the galaxy surveys, and that requires some change in physics.
That would be really interesting.
We will see.
Because all this data which was showing low was sigma 8, all that comes from smaller scales.
That's right.
So that's
Yeah, and just to give you a sense on how the data is improving, these are plots we like to look at, which is how deep the survey is, what the noise level is in microkelvin. This is the level of Planck, about 20 or so microkelvin in the co-ed, all the Planck data co-eded. This is the fraction of sky coverage up to about 20,000 square degrees. Remember, the sky is about 40,000 square degrees. The part that's usable for CMB analysis is about 25,000. This is where we were with the ACT DR4 data, which is most of the analysis we've published. So there we had about 4,000 square degrees that were more sensitive than Planck. Now we're here at the yellow line. We've got about nearly 20,000 square degrees more sensitive than Planck. All of it at 5 times the resolution, and a lot of it, roughly 14,000 square degrees at half the noise. So it's and you can see how big an improvement it is over our earlier data. And this is the measurements in temperature. This is the measurements in polarization. This is where Simon's observatory will be. Advanced Simon's observatory is here. Here's Simon's, and with the NSF funding, we're now about there. And this is the CMBS4 target. So the data is really improving dramatically. These are our lensing maps. So this is a map of the dark matter fluctuations. Those of you who can do Fourier transforms in your head can pull out the power spectrum. Here's more lensing maps. Give you a sense of how much things. So here's the level of noise in the Planck data. Here's the level of noise in our maps. Here's the signal. And you can see we're signal dominated to about L of 200 and looking at about enough of the sky that the signal to noise is in the lensing signal, I think it's about 50. And that translates to a 2% measurement.
Why is it maximum at 30?
Why is the power spectrum maximum at 30? Because
This is lower redshift than ZMA.
Okay, it's a good question. Can people see this board? I don't know how wide it is. Should I write lower? Where should I write?
Oh, that's okay.
Right here? So, okay, when we we're used to looking at the power spectrum P of K, which peaks at a wave number of about 10 to the minus 2. The lensing signal is a displacement. We get 2 factors of K squared. So it shifts the peak over. And then the distance to the surface of last scatter, I have to work backwards to where this peak is. Let's see, the distance to the surface of last scatter is about 13,000 megaparsecs. The lensing signal is about halfway in the middle, because that gives you the most deflection. So call that 6,000 megaparsecs. And then you divide 30 by 60, and that, so the wave number that this is peaking on is 30 over 6,000, so about 0.0005, and that produces that feature.
It's just the usual transfer function, only slightly modified.
That's right.
Okay.
Speaking of Fourier transforms in our heads, that map you're showing looks like it's been filtered or something to some set of frequencies, because it looks like ripples in a pond.
Yeah, it's filtered about here.
I see, and so we're seeing that kind of edge of your filter.
Well, the peak is here.
Yeah, but
So,
still,
It's,
I mean, you can definitely see there's a filter.
there's a characteristic
applied,
difference.
yeah.
Yeah, these are fun. So here's the app lensing map. So that's the integrated mass. This is the CIB measured from Planck. So you can see on the scale of the visible universe, the light traces the mass. That's 10,000 degrees. Those of you who believed in things like Mond, that you expect to see an unusual relationship between light and mass, need to explain this. You know, the lens and power spectrum. Yeah, so there are the error bars. So we'll have it, we've underlined it and seen segmented. So it looks good, things look really good. We have lots of null tests, we pass them. That's not the results, just the error bars. That's around lambda CDM.
And did you say when it was going to be announced?
Soon, like a couple, like 3-4 months. We have to. These people, when I was running these things, they go faster. So, yeah, so I've already advertised that. Okay, so that's looking at dark matter. Now it's looking at tracing the electrons, and these are some slides from Manu Shine. And the idea here is, let's look at the night sky. And this is the night sky around Andromeda. There's the Andromeda galaxy. This is the distribution of electrons around Andromeda. If you look at absorption lines to quasars and look at the gas, you see here's the Milky Way. That's the gas of our own galaxy. You see how far out the gas extends in the intergalactic medium. This is not our work. This is from quasar absorption lines from this group here.
Which is what? HST of the UV.
HST UV. And this reminds you that gas goes far out. And there's been this something we've known for a long time, that you sum up the amount of mass in galaxies and stars, and it doesn't account for most of the baryons. There's nice work that there's this that Fukahida and Peoples did 25, 30 years ago, of just counting up the baryons. And they're just, most of them were not in stars and galaxies, are in gas. And what we now understand is that that gas has been driven out by various feedback processes. And that changes the distribution of matter, it changes the power spectrum. It has to go back to Andre's point about power spectrum and lensing measurements. It suppresses power because you've driven matter out. And this is the amount of power suppression you see due to gas being expelled. This is fractional power spectrum. And these are a whole bunch of different cosmological simulations. And different simulations give you different ideas on how much the power is being suppressed. And this gives to about this rise to about a 30% uncertainty on the matter power spectrum on some of the scales probed by the Rubin telescope and by lensing surveys. So baryon feedback is a really significant uncertainty. And what's cool about this kinetic Sunyaev-Soldovich effect is it's going to give us a way of measuring the distribution of electrons around galaxies. And the idea here is that if you've got a cluster of galaxies moving towards you with gas, then the stuff moving towards you makes the gas hotter. It's scattered up in energy. It's moving away from you, scattered down in energy. And that the signal is proportional to the optical depth here times the velocity. We can predict what the velocity should be because we know how galaxies move. We made the first detection of this back in 2012 in actually Nick Hand's senior thesis, where we looked at pairs of galaxies and noted that the one that is further away in redshift, which is moving towards you with this kind of geometry, was consistently hotter than this one. And we stacked them all. And we can now use this to get a measurement of the gas distribution. So this effectively counts all the free electrons. Compared to the thermal SE effect, it's sensitive to lower mass halos. It's a relatively small effect. The typical signal is about 1/10 of a microkelvin. Remember the CMB fluctuations that Kobe or WMAP or Planck sees have an RMS of 100 microkelvin. So we're looking for a signal that's 1,000 times smaller than the CMB fluctuations. It's kind of funny, like when I started this, the CMB fluctuations were what we're trying to measure. We always say how small they are. And now this is our really noisy background that we have to get away from. And we get away from that in a couple ways. One is we're looking primarily on smaller scales, where the CMB amplitude as we go to higher L smaller scales drops. This is the noise level. Actually, that was that characteristic noise you saw for the survey. This is the CMB signal. This is the level of the KSE signal. And you can see if we go to these scales, here in particular, the KSE becomes now only a factor of 50 to 100 smaller. So now what we do is we take a survey like BOSS that has hundreds of thousands of millions of galaxies, and we stack them. We stack the signal on all of those, and that lets us reduce it, and that's effectively measuring the cross correlation between the galaxy halos and the surrounding electron distribution. And here what we did was we took the CMAS survey and we just stacked the gas on it, the CMB on it, and you can see the stacked signal.
And what does CMAS stand for? Maybe you said it, I missed it.
CMAS is a sample within the BOSS galaxies sample. I don't know what it stands for. It's somewhat large, it's big galaxies in the sample.
And BOSS is SCSS4.
It's SCS4. And with that, we can now measure the distribution of gas. And this is the key plot I wanted to get to, which is the KSE signal. So what we get for this signal, hot and cold signal around the centers of galaxies as a function of distance. And this is our measurements at 90 and 150 gigahertz. We get a consistent signal that shows the effect of the electrons around the clusters. And you can see the suppression due to the electrons. as a
Distance
function of
from
this.
what, sorry?
This is from 0 to 6 arc minutes.
Distance from what? From the center
The
of the
center of the cluster,
from the cluster of galaxies.
from each galaxy, center of each galaxy.
Okay.
So you take each galaxy, you stack the CMB signal on it, and you're measuring the suppression due to the KSE effect. Hansen.
So this is how far gas, or rather electrons stretch away from the center of.
Right, and this is how the dark matter is distributed. So you can see for these size galaxies, the dark matter is typically, this is in co-moving radius, the dark matter is typically within about a megaparsec. The gas is kicked out 2 or 3 megaparsecs. The gas is kicked out much further. And interestingly, it's kicked out much further than any of the hydro simulations currently predict. So there's there's more energy in winds than people have estimated. And remember, kicking gas out changes the power spectrum. So the baryonic effects seem to go out further. And to me, what's exciting here is we're directly measuring the electron distribution around a set of galaxies. We can do this at many different redshifts. It's a redshift independent effect. And as we can have larger and larger structured surveys, we can really test this a model and measure how measure the effects of energy change.
The KSC is I'm asking for Yassine here because he's shy.
Okay, I'll ask a question.
Go ahead.
It's proportional to the velocity of the gas.
Right.
So if you just stack, it would just cancel out.
We stack it weighted by velocity. So what we do is we take the large-scale structure survey, we predict what the velocity should be. And that's work that Shirley Ho has led. It's the same codes as the reconstruction. And given the predicted velocity, we stack with them. We weight them by the predicted velocity.
And you predict the velocity just from like the continuity equation.
It's more sophisticated. They use a machine learning thing, I think.
So we should trust it.
No, we actually not, in this analysis, we're just using linear theory.
It's like linear.
It's a combination of the continuity equation and the growth of structure equation. You know, the velocity is equal to the gradient of the potential.
The ionization fraction, does it change? Or?
It's all pretty much fully ionized. So, you know, if you add up, I mean, this gets back to the missing baryon problem. The fraction of gas and neutral hydrogen is very small. So I think you look at galaxies in this mass range, you know, there's roughly speaking 10 times as much mass in stars as there is in neutral hydrogen and electrohydrogen, and roughly 5 times as much of the mass in ionized gas as there is in stars.
So what kind of galaxies are these that,
Massive elliptical galaxies. These are
but not the clusters that you?
not the
were
clusters.
previously-
These are massive elliptical.
You do one mass spin for all the galaxies, or?
I think for this analysis, we did 1 mass spin, because it's so signal to noise 6. We'll have a new, this is with the DR4 data. The DR6 data will have hard signals, but we've not done that analysis. And this is sort of fun. These are simulations of how we expect the mass to be distributed, the gas and the starlight. And these are actual stack data for these CMAS galaxies of the distribution of mass from the lensing, the distribution of electrons from the KSE, and this is a zoomed in picture showing a particular galaxy. And just sort of a reminder that when we look at galaxies, and that's what I was trying to get at with the picture of Andromeda earlier. When you look at starlight in galaxies, you're really looking, you know, take our galaxy, most of the starlight is coming from within the solar cycle, within 8 kiloparsecs. the characteristic scale for the mass is more like 200 kiloparsecs, and for the gas is more like a megaparsec. So when galaxies are a sense, if we think about them in terms of the electrons, much bigger than.
So this is where most gas is. at
Most
the
gas
megaparsec.
is in the megaparsec scale, and this is consistent with what people have inferred from the absorption lines measured with the Hubble.
But you said it's ionized, what absorption?
Metal lines.
Or metals?
So they measure the metal lines, things like carbon lines, and infer the distribution. We have the advantage, we don't have to make assumptions about gas levels. But it's a consistent picture.
David?
Yep.
Why is your gas stacked image not symmetric? If you stack it, you would think it would just be nicely symmetric. It's like more red on the bottom.
I think this is actually real data without that much filtering, and you're just seeing how much noise there is in the largest modes. Because remember,
It's only
CMB,
6 sigma, right? Your result's only 6 sigma, so it's gonna look like hell.
It's just it's just noise realization.
it's the CMB realization that we happen to live in, and it's to go back to what the noise looks like. It's really right. We're sitting here on these scales, and my noise spectrum looks like that, which is the CMB. So it's a really red noise spectrum.
By the way, Ichiro Komatsu was here was at CCA 2 weeks ago, talking about measuring the temperature of the gas, and that all without using the metal line. So it all seems to hold together that there really is this very hot component.
There's a lot of hot gas out there, and I think the simulations are currently not injecting enough energy in to get it right.
Yes.
And I wonder when it's ejected. Whether it's actually a lot of it may be ejected at relatively high redshift. And it'll be interesting to do this as a function of redshift. And but let me end by talking a little bit about this cluster temperature measurements. And this is kind of cool because you can take in addition to the TSE signal, there's a higher order term. That's a relativistic term that you could compute, and what you're effectively do is you can then take, let me just skip because it's more legal type questions to the results, and this is fun. So these are taking 2 samples of TS clusters detected with the thermal FC effect. So it's measured with different values effectively of Y. And then inferring from it the mean temperature. And we can see that we have an inference of the distribution of mean temperatures for these from the relativistic effect. And, this, I'll skip this and take questions. But just leave you with sort of a sense of where I feel we're going with this work in the CMB, which is basically the history of this field is that we mostly use the CMB to study the universe at redshift of 1100. What I wanted to give you a sense of is we can now, with small scale measurements of increasing sensitivity, we're now in the position where we can really start to do detailed quantitative measurements of what's happened to the photon between the surface of glass scatter and us. The most sensitive ones we have right now is our lensing signal, where we're talking signal to noise of close to 50, which means that we're really starting to make precision measurements of the mass distribution. But we're now starting to do this with the hot gas, LLC, with the electron distribution, even with this relativistic effect. And the CMB, in the coming years, I think will be an important probe, not only of the early universe, but particularly when combined with large-scale structure surveys. Right? And you notice that a lot of these things are done in cross-correlation of measurements of some of the really fundamental things, right? We're measuring the integrated mass, the integrated electron density, the integrated electron pressure, the integrated temperature. And so from that, we can learn interesting things about the properties. So
If there are interesting things.
I think we know they're interesting things. I think one of the great things about cosmology is we know that dark matter is there, and we know that the dark matter is not explained by physics as standard model. So that's got to be interesting. We know dark energy is interesting, and we know the origin.
Dark energy, come on, it's lambda.
Well, still, that's interesting. That's beyond the standard model. We'd like to be convinced it's lambda. We don't know that we will discover what the dark matter or dark energy origin of the properties are, or the origin of fluctuations. So those are what I consider the home runs that we could hit from these measurements, and that be what one should swing for home run. What's fun for me with these measurements is there's also lots of what I would call intellectual singles or doubles. It's interesting. I think it is worthwhile to understand the physics of feedback, to understand how galaxies form. And I think to be able to measure things like the thermal pressure, use a cluster effectively as a bolometer to measure energy injection, to look at the distribution to measure momentum injection, means that we can now measure these integrated properties of how feedback affects the environment. To rant a little bit against galaxy formation and field, I find, optical astronomers often tell like what you want to like. I want to know from an observation, what are you actually measuring? Are you measuring the pressure? When someone gives me an observation of some high redshift galaxy, what does that tell me about energy injection? How do I interpret it? And what I like about these measurements is I understand what integral PdV is. I understand what the integral momentum is. And I think it's much easier to compare these kinds of observations that are integrated quantities on large scales to the observations than some of the work that people do with measuring galaxy spectrum. My bias is I spent most of my career thinking about the sea.
Are you done?
I think I'm done.
Please.
In this room, a lot of people are interested in interesting things going on in the dark sector. And if there's issues with sigma 8, that's very interesting from a dark sector perspective. And if there's issues with where the gas is, that's also potentially related to the dark sector. What do you think are the most, I think it's sort of interesting to ask, what are the directions of like dark sector new physics that are most interesting to look at here?
So one I didn't talk about, which will have some interesting things to say in the next few months, is we'll have a much better measurement of the primordial power spectrum, particularly the polarization spectrum, to Ella 2000. And that's sensitive to how some dark matter properties, for example, dark matter baryon interactions, dark matter decay, annihilation signals, anything that's changing the properties of the way recombination is happening at redshift 1100 in detail shows up there. So that's one, it is a way of getting at some dark matter physics that will have some better measurements there.
But those same effects happen line of sight. If there's annihilation happening over line of sight, if there's dark matter baryon happening over the line of sight, those should also, I think, affect these observables, right?
Yeah. I think for dark matter baryon interactions, that may be something where study of dwarf galaxy and fall may be a better one. I'm not sure the KSC measurements are the best, though I haven't been a while since I looked at that.
I mean, if there are dark matter baryon interactions, the baryons should heat up if the dark matter particle is heavier than the baryon.
Yep.
So,
No, absolutely. But I think that's easier to look at
It
redshift
might be, yeah.
1100 because we don't have any other form of energy change.
yes, exactly.
So
yeah.
the challenge here is separating that from energy input from AGNs and
Fine,
stars.
yeah.
So I mean, it would have the effect, but it's the earlier time is cleaner.
More questions? Please.
Just at the beginning, I missed one of the simplest points. You said that you have the unlensed and lensed can be, but we don't know the unlensed one.
Right.
I mean, how do we? But then it seems that we.
So let me go through the estimator. Put on the lights. Here. I ready for this. So,
Can you raise this screen?
no, this is.
All right, up or not?
So the way to think about this is the temperature we measure is, well, temperature point N is the unlensed temperature map with a displacement, right, where this is the displacement field. If I look at this, if I expand this out and then look at it in Fourier modes, the temperature, the lens temperature is basically the unlensed temperature at K prime times the deflection field at K prime minus K. So if I have mode law coupling instead of that. Actually, the linear order term is just the unlensed. This is the determinative term. So what we can do is write down an estimator for this. And the estimator for this is that the deflection field, now let's just call it Q, to not confuse that, can be estimated by computing the temperature of the lens map at mode K times K plus Q summed over Q. So we're basically using summed over K. Summed over K. So we're using the lens field. So remember that this field was Gaussian, had only a 2-point function. This lens field is computed from the square of it. So this field now you're computing this from the non-Gaussian AD. And these are this is a noisy estimator, but you sum over a lot of K modes. And with enough K modes that you sum over the map, you can see that we can get pretty good signal to noise on that lensing map.
Is it actually done that way still, or do people do a forward model with, like, or do they literally compute an estimator like
They
that?
literally compute an estimator like that. And this is something actually that Yassine and I were discussing earlier about how we do estimators. I think a lot of people now are trying to do very sophisticated things with likelihood functions and forward modeling and so on, and using machine learning and all these things. It's very dangerous because to do a good forward model, you need to know your model very well, and you need to know your noise. And what's nice about an estimator like this is you can make this estimator only with cross correlations. So what we actually do is we generate 4 different temperature maps. You could think about this as we take our data from Monday to, we make a map of all the data we observe on the first day of a month, and first plus fifth plus ninth, second plus so on. So we make 4 independent maps. each of with independent noise. Our dominant source of noise is the sky. We don't know how to properly model atmospheric noise, and it is non-Gaussian. So we want it to drop out. So we take maps from one day and correlate it with maps from another, so our noise properties are independent. And that does throw away a bit of signal to noise because we're missing the autos. But the autos require understanding the noise properties really well. And I think this would be my general rule for observations. When you don't understand our experiments, when you don't have really accurate noise models, rely on cross correlations. This is something we learned from our CMB work on the ground. You know, Raphael Flauger and May Lozic and I pointed out in the Planck first year maps there were problems, and those arose because the detectors were sitting in the same cooling unit which were vibrating together, producing correlated noise. I've just seen this in a lot of experiments where you don't know your noise properties well, that it's just much safer to do the kind of unsophisticated things and rely on the cross correlations. Yeah, I mean, I am spending a chunk of my time now thinking about machine learning applications to cosmology, and I think it's a very promising area. And there are a lot of excitement about machine learning. But my warning in using it is if you're doing forward modeling, you really better understand your experiment systematics that you're modeling forward really well. Otherwise, if you can learn you can get fake signal. It's good to have these kind of traditional, more robust methods to complement.
Is there an implicit assumption that the CMB is, yeah,
But we test that in other ways. And, you know, it could be that the
the thing I think that would a sort of simplistic way of describing it for non-experts be that if there's non-Gaussianity, it would be, well, first of all, in models, you would see that the foreground will produce non-Gaussianities, and therefore you attribute it to that. And
well, one nice test of this was that figure I showed, where the fact that, let's say there were primordial non-Gaussianities, that would give us some deflection signal that was wrong. It'd be really strange if that deflection signal from the primordial effect of redshift of 1000 traced the distribution of infrared light. So the fact that it's a one-to-one mapping between infrared light and the deflection field is yet another measure.
right, that seems like the more intuitively, the more easy way to think about it.
Yeah. Andre had to leave. More questions for David? Let's thank David again.
Thanks.